Welcome to part 3 of my video series on reinforcement learning for Connect 4. If you haven't watched the first and second videos, please do so. In those videos, we build the Connect 4 game from scratch, but also we build a basic reinforcement learning bot using deep Q learning. In the second episode, we implemented experience replay and double deep Q networks for better and more stable learning for the bots. And in this episode, we're going to go over an improved self-play training method. So let's get started. Self-play is a method for RL bots to learn a task by playing against itself. Bots learn by trial and error in this method without us having to supervise or instruct it on what is right or wrong. We're essentially just feeding it the rewards that we build out in our reward system. In self-play, our responsibility is to set up the curriculum, let's call it, for how the bot performs self-play. In our current implementation, we have a very basic self-play method where our bot is playing against itself while learning from both sides of the board. So imagine you playing Connect 4 by yourself and pretty much just placing the pieces for both sides, red and the yellow. Both players are performing training loops here and updating parameters, and what we saw was a 50-50 split in win rate, which was kind of as expected. Both networks, or the same network, was essentially learning from both sides of the board and not really settling on a specific strategy to play against itself, because the parameters of its value function were essentially always updating, and its understanding of the game and the values of each action and each state was changing every time a move was made. So to improve our self-play curriculum, we update it as follows. The RL agent will start a training loop against a random bot for 1,000 games, and once a minimum loss threshold is reached, our early stopping mechanism that we implemented last episode, we stop the training loop. Next, we'll store the current bot's parameters in a sort of cache if the win rate for the current bot is greater than some threshold. So if more than 55% of the time the bot was winning against its current opponent, then we store the current parameters in the cache. In the cache, we'll store a certain number of opponents, let's say, and maybe that's 7, maybe that's 10, maybe that's 20. That's kind of up to us to decide. And then we'll start a new training loop. And for each game out of 1,000 games, we'll randomly select an opponent to play against from the opponent cache. And this way, our current bot that we're training doesn't really know which opponent that it's going up against. We're interested in this randomization because when we train on an opponent that the bot sees over and over again, it can start to overfit on a specific strategy that might work for this bot, but in general might not work on the grand scheme. When we select an opponent, the opponent is set to test or eval mode and does not update the parameters. So we don't run any training loops, we don't update any parameters in the neural network, and we also use pure exploitation for this, or no exploration, where we set the epsilon value equal to 0. So there's never going to be a case where we select random moves. We only trust the parameters of the value function, which is a neural network in our case. And then we just repeat this for a certain number of rounds, or we'll call them levels. So in this implementation, we set the training parameters for self-play as follows. We'll have 50 levels. Games per level will be set at 1,000 with early stopping enabled. And the opponent cache size will be set to 10 opponents. The threshold win rate will be set to 55%. And again, these are arbitrary. These are kind of up to us to decide based on testing and what we see through the results. To better visualize this, we have this diagram, and the gray box represents the environment to which our RL bot plays. This represents our bot with replay and a double DQN network. The green dots sort of represent the states, actions, and rewards. And how this works is when we have a state, let's say the initial game state, we feed this into the bot, which contains a value function, our neural network, and this outputs some action. Based on this action, we're going to take the action, send it to the environment, receive a reward as well as an updated state. These values get stored in our memory of size 1,000, so the 1,000 last experiences, let's say. These are randomly sampled into a batch size of 200, and those batches are used to update the parameters of our neural network. This is one of the main changes we made in the last video to help stabilize learning of our bot. When we make a move that leads to a new state, we also feed that new state into our opponents that then have to make another move themselves, which updates the state. And in the sort of opponent bot's square here, we have a cache of, let's say, size 10. So we're storing the last 10 trained opponents in this cache. And when a game starts, we select a new opponent. This opponent's value function estimator will be used to select the next actions based on the state that is fed to it. Anytime this action updates the state, then this again is just fed to our bot, who then makes another move and the game continues. If in any case our bot takes an action that leads to a game that is finished, actually this game done should be over here, or if our opponent bots make an action that leads to a game that is done, then we'll select a new opponent, and then that opponent will be used for this value function. Basically from this cache, we're randomly selecting them anytime a game finishes. This is our training loop for self-play. We have the number of levels, the games per level, 1000, and we initiate the initial players, which is RLBot, DDQN, and the bot, which is just randomized. And these are just string values because we have to actually initialize the classes. The opponent cache is going to be a deck or a DQ, and we'll set the size to 10 opponents for now. And then for every n in range of levels, which is this 200, we will run the main game loop, which runs 1000 games of Connect 4, and we'll return the players and a win rate for the first player. If the win rate is greater than 0.55, then we will append that player to the opponent cache. Otherwise, we'll just reset the players to the current player and a copy of the current player as well. So this is on a high level how this works, and let's take a deeper look into the main game loop. There's a lot of setup involved, but near the beginning of the main loop, we check if the loop is currently on self-play mode, and if so, then we'll explicitly set the players to P1 and P2, where the RL bot that is trained is always going to be -1. We use the while loop to run a game of Connect 4, and after a few event checking, etc., and making the bots move, we check if the game is done, so a win or a draw is reached. If that is the case, then we'll simply just replace player 1, so this is the second player, not first player -1. We'll simply replace player 1 with a random sample of size 1 from the opponent cache. When the training level is done with 1000 games, or we've early stopped, then we'll set the out players equal to the first player. We'll do a reset, and we'll get into that a bit later. And then we'll just set a deep copy of the player as well. And we'll return these out players as well as the win rate for the current player 1. To reset the bot after every self-play training level, we define a method here that is called up here. And we're essentially just resetting a lot of the parameters and some tracking stuff for the bot. So here we reset the learning rate. We haven't really applied any learning rate decay, but maybe in a future episode we'll do that. We decay our epsilon rate, so we're just going to reset that back to 0.3, for example. We reset our losses that we track as well as the rewards, number of moves, number of epoch moves, as well as these administrative things we set, as well as setting the models, both the main model and the target model, to eval mode. We'll also resync the target model back to the value model's parameters. The whole idea of self-play is that the bot can learn specific strategies against certain opponents, and once it gets better up to a certain point, and that point is defined by us based on early stopping, then we can put the bot against even tougher opponents, which aka is itself in past iterations. And that way, when it learns a new strategy, we can train it against those very strategies so that it can learn even more strategies to better its play in Connect 4. It's really quite intuitive. Let's get into a review of some of the games. So in this setup, we're just in testing mode, and this is the first level of the RL bot self-play training. So this bot here was only trained against a random bot for about 1000 games. Yeah, we can see it doesn't do very well. I mean, it definitely has a preference for a side. It seems like I'm playing like a random bot, and when I make random moves like this, it has a certain preference towards the outside edges of the board. Maybe that's just what it learned in its time of training. Really, the neural network parameters are randomized at those times, so it may be the case that the parameters just so happen to produce higher values to start for columns 1, 2, and 6 and 7. And that's kind of why it has this preference against those sides of the board. In episode 1, we kind of showed the training loop for this bot, and the strategy that it learned was to just place all its pieces in a single column. Playing against a random bot, that's really how to win. There is no predictability in its moves, so you might as well just place all your pieces in a single column, and that should net you a win on average against a random bot. But here, what we do see is that when I place pieces in a single column, the bot doesn't really know how to respond to this. And we'll try this with column 2, column 1, maybe column 3. It really works for most columns. Let's see if maybe there's a column that it doesn't work on. Oh, okay. Well, it kind of likes column 6 and 7, so maybe that's why it doesn't work as well. I mean, it still does though. This makes a lot of sense because stacking the pieces like this was not a strategy that it was trained against when it was trained against the random bot. The random bot wasn't doing this, so it doesn't really know how to respond to this because it never had to deal with these kinds of states. This bot was trained on 50 levels of self-play. Maybe it's moved its preference towards the center of the board, but there's no clear indication of strategy. Yeah, and this is me playing like a random bot. Now let's try that previous strategy where we were placing pieces in the same column. And it doesn't really know what to do here as well. I mean, it has an interesting idea to just play the center, which is probably how you win these games. Intuitively, you'd want to set up like a trio like this to then be able to have an unstoppable connect 4, because I can only place a piece here and you can just place a red here. But it still doesn't really know how to respond to these situations. Let's try a different column. Second column 2. Oh, okay. So it intervened there, but we know that it kind of prefers the middle ground here. This one as well. But still, it doesn't really know how to respond, but there's definitely been a change in how it's playing. But yeah, we still have a lot to play with in terms of the size of the neural network, the hyperparameters that we used, as well as this actual self-play mechanism. Even in the actual algorithm of deep Q learning, there's a lot to kind of improve there. I'll leave this video here for now, make it a bit shorter, and hopefully I'll see you in the next one. Be sure to leave a like, maybe comment if you found this interesting, subscribe as well if you want to see future videos on this bot. And yeah, I'll see you in the next one.